Hi, ladies and gentlemen. 10.2 is entitled Simple Machines. Our life is pretty much filled up with all sorts of simple machines. And a simple machine is something that either makes the force bigger or smaller, or it changes the direction of that force. Kind of like a pulley. A pulley changes the direction of the force, and levers can multiply or divide our forces. There's a lot of debate as to how many simple machines there are, but we typically accept that there are 6. The lever, the wheel and axle, a pulley, an inclined plane, a wedge, and a screw. So these are the 6 different types, and I found a couple pictures here of pushing a box up a ramp. That's an inclined plane. Using a hammer to pull out a nail. That's a lever. Hoisting a flag using a pulley. A wheel and axle. A wheel and axle is when you have a larger wheel around a smaller axle. So like a screwdriver, you know how you grab the outside barrel of a screwdriver and you turn it and it turns that inner axle? The outside and the inside. Or like a crank, a steering wheel would be the gears on a bike. You have a very large diameter wheel and a very smaller diameter axle. Now you can use those in reverse too. You can turn the small axle to get a very large angular velocity out of the wheel too. The wedge. Driving a wedge down through a log, and then a screw like a jack, like turning up something to a lot of these are in your, if you go into your basement you can find these things. These are to support your house, this jack right here. And don't think a lot of people think the screw, the only simple machine for a screw is a screw. That's not really true. A screw is something that you turn that separates, or you turn it and it pulls it together. So the actual screw itself, it isn't really a screw. The action that when you turn it, the end pulls together the 2 pieces. That's what a screw does. And along with levers, there are actually different types of levers. This is what's called a first-class lever, when you put the fulcrum in between where you push and the object that you're lifting. So like if you push on one side and it lifts up the other side, much like you would with this rock, that's a first-class lever. A second-class lever is when you switch the location of where the resistance is and where the fulcrum is, like a wheelbarrow. On a wheelbarrow, you lift on the end, but the pivot isn't in the middle, the pivot is on the other end, and you put the load in the center. The wheelbarrow is a classic example of a second-class lever. And then the third-class lever, you switch the place of the resistance and the motion. So you no longer are lifting on the end, now you're lifting in the center. Kind of like this steam shovel that's in this picture here. The pivot is right in the center, and then you lift by pulling on this guy in the center. So the string is lifting, and then the load's on the very end. First-class lever, second-class lever, third-class lever. There's a bunch of different terms that we're going to have to define when we start talking about simple machines. And I've got them labeled right here. A machine, first of all, it's an object that changes the force or the direction of the force. So it changes the magnitude of the force or the direction of the force. Now the effort force, this is what you, the user, put in. The resistance force, that's the force that you're trying to overcome. Like in that first-class lever where we were prying up a rock, the weight of the rock would be the resistance force. Like if we were lifting in this pulley here, if we were lifting this thing here, the weight would be the resistance force. This force that we pull down, that would be the effort force. Mechanical advantage. The mechanical advantage is a ratio of how much force are we getting out. It's the force of resistance, Fr, divided by the force that we exert, Fe. So you take these two things divided by each other, the resistance force divided by the effort force, and that's going to give you mechanical advantage. A mechanical advantage of 1 would be something like this right here, that if this was 10 pounds, we'd have to pull down with 10 pounds. Now that's in an ideal world. In reality, you're probably going to have to pull down with like maybe 10 point something. Because number 1, this pulley has weight, so you have to spin it up, so there's some inertia that you have to overcome. And number 2, there's some friction in between that bearing. So having mechanical advantages of 1 it's good, but you have to watch out for, stretching of objects. Like string can stretch. There's friction there, and then there's mass to overcome, starting it to spin. Now, effort distance. This is the distance that we have to put in. So a lot of times you don't get anything for free with with simple machines. You get you put the same amount of work in that you get work out. So you exert a lower amount of force, but you have to do it over a much larger distance. Like for instance, with this can opener up here, you have to put in just a little bit of force, but you have to turn this thing a great deal of distance, and you get out a much larger force, but a smaller distance. So the work ends up being the same. Actually, the work you put in is going to be more, and we're going to get to that, and that's called efficiency. If you put in exactly the same amount of work that you get out, it's 100% efficient, and there's no simple machine in this world that is 100% efficient. Effort distance. So this is the distance the user puts their force in. Resistance distance. This is the distance that your load travels. Now, the ideal mechanical advantage. The ideal mechanical advantage is different than the mechanical advantage because it doesn't take into account friction and all this other stuff, stretching, twisting, inertia. It only deals with it. Ideally, this machine should do this. And what you do, it's the distance that you exert. So it's the distance of, what do we call effort, divided by the distance of the resistance, R, dE divided by dR. Now, efficiency. Efficiency, if something, the bigger the percentage of efficiency is, the better the machine is at taking the work that you put in and changing it into the work that you get out. And I actually copied these right from our book right here. Efficiency is the work you get out divided by the work that you put in. Now, if you get out exactly the same amount of the work that you put in, so this number is the same as this number, it's 100% efficient. And again, it's impossible to have something that's 100% efficient, and we strive to get it as close to that efficiency level as possible. Now, remember also that the work out, so that's the force times the distance. So that's out is the force of resistance and the distance of resistance. And the work in can also be written as force times distance. So that's the force that we exert divided by times by the distance that we exert. So another way to write this, if you kind of notice, dr over dE, look at there, these are almost the same. If I just flip this one around, that's why you put the IMA on the bottom, and then FR divided by FE, that is mechanical advantage. So another way to calculate efficiency is to take the mechanical advantage and divide by the ideal mechanical advantage down here. So these are ways we can find efficiency. And you always multiply by 100, because if this divided by this is 0.5, multiply by 100 and you get 50% efficiency. And then lastly, a compound machine. A compound machine is something where we combine more than one simple machine. A combination of machines. Like a bicycle. A bicycle has tons of simple machines built into it. And if you're ever dealing with a compound machine and it says find the ideal mechanical advantage of this compound machine, you multiply the constituents of. So the ideal mechanical advantage of a compound machine is just the ideal mechanical advantage of machine 1. You multiply it by ideal mechanical advantage of machine 2, and then so on. Same way with the mechanical advantage. The mechanical advantage of a compound machine is you just multiply the constituents of it. So it's the mechanical advantage of machine 1 times the mechanical advantage of machine 2, and then so on. A lot of words that we're introduced to here. I've got a picture here of the 6 simple machines and how we find the ideal mechanical advantage of each. So in a lever, the distance that we exert is this distance from here to here, and then the distance of resistance is this distance over there. An inclined plane is this distance here, the length, divided by the height right there. With a wheel and axle, the distance that we exert, it depends on, like here we're putting our force of exertion here, so it's this radius divided by this radius. With a wedge, the distance that we're exerting down this whole length, and the distance that we get out is that right there. A pulley. Pulleys are kind of tricky. The way that you deal with pulleys is you find the load. So here's the load, and you figure out how many ropes are supporting it. So right here, you'll see it's got this like little line here. There's one wheel supporting it. So this has an ideal mechanical advantage of 1. See how this one has 2 ropes supporting my load? So this has an ideal mechanical advantage of 2. This one here has 4, so this has an ideal mechanical advantage of 4. Meaning that if you had this guy right here on the far right, we could, if this was maybe 100 pounds, ideally we only have to exert 25 pounds to lift this mass. We're probably going to have to do more because of friction between all these pulleys, and there's stretching in the rope, and then these pulleys weigh something, so they have to get spun up because of remote rotational inertia. But ideally, it's got a 4 ideal mechanical advantage. And I'll set some of these up in class so you can actually see them. And then lastly, with a screw. With a screw, what we're doing is we have to turn this thing all the way around, so that's why it's 2 pi times the radius, and the radius is the length of this lever. So we have to turn this thing all the way around. That's the distance that we put in. And then the distance that this thing goes up is just the spacing between 2 of the threads, and they call it P. So 2 pi times L, because it goes all the way around, and it goes up this much. So this is how you find the ideal mechanical advantage of all the 6 simple machines that we're going to be dealing with. It might be a great idea to print this off rather than trying to copy everything down that I'm saying, because there's just so many pictures, and it's so helpful to be able to refer back to this. And then lastly, the last thing I want to do with you is just an example problem. This is from your book. It's example problem 4. It says you examine the rear wheel on your bicycle, and it has a radius of 35.6 centimeters. It's got a gear, and this gear has a radius of 4 centimeters. When the chain is pulled with a force of 155 newtons, so there's a chain coming off this, so there's 155 newtons. The wheel rim moves 14 centimeters. So this thing moves 14 centimeters. The efficiency of this part of the bicycle is 95%. So the efficiency equals 0.95. So number one, what is the ideal mechanical advantage of the wheel and gear? So we're going to refer back to the ideal mechanical advantage of this guy right here. It's where we put our effort force. We're putting the effort force not on the outside rim in this case. We're putting the effort force on the inner gear. So the ideal mechanical advantage is going to be this radius 4.00 divided by this radius 35.6. And it's okay to have an ideal mechanical advantage less than 1. So 4 divided by 35.6, 0.112. Now these don't have any units. Part B, what is the mechanical advantage? Now remember, the mechanical advantage is the force that we get out divided by the force that we put in. I believe so. I'll double check it. So force of resistance divided by the force exerted. Yeah. Now, I know right away that the force that I'm exerting is 155 newtons. Now I have to somehow figure out the force that I'm putting in. And I just had an idea. I don't think I'm going to be able to figure this out. I think what I'm going to use is the efficiency. The efficiency is my mechanical advantage divided by my ideal mechanical advantage. So I look down here to make sure, yeah, mechanical advantage divided by the ideal mechanical advantage. And I know this. I know that my efficiency is 0.95, and I'm looking for the mechanical advantage, and I know that the ideal mechanical advantage I just found is 0.112. So if I take my 0.95 multiplied by 0.112, I get 0.1064. So my mechanical advantage is 0.1. 0.106. Part C. What is the resistance force? Ooh, now I think I'm going to use this down here. I know that my mechanical advantage is 0.106. I know that the force of resistance is what I'm looking for. And I know that the force I'm exerting is 155. So if I take 155 times 0.106 times 155, I get 16.5. So my force of resistance is 16.5 newtons. That's how much this thing is opposing me right here. This thing is opposing me with 16.5 newtons. Part D, how far was the chain pulled to move the rim 14 centimeters? How far is the chain moved to pull this 14 centimeters? Okay, I think there's a couple of ways to do this. I think I'm going to do it in terms of a proportion. So I'll do a proportion. 14 centimeters is to this whole circle as how much of this is to this whole circle. So I'll do 14 is to the whole circumference, which is 2 pi r, as I don't know how much of that circle, x, is to its whole circumference, 2 pi times the radius of 4. So I cross multiply and divide. So I get x times 2 pi 35.6 equals 14 times 2 pi 4. And you'll notice it's kind of nice that this 2 pi business cancels out. So 14 times 4 is 56 divided by 35.6, so I can figure out how far this thing had, how much chain I have to pull. So 14 times 4, 56, divided by 35.6, 1.57 centimeters. Because this is all in centimeters. This is 35.6 centimeters of string. This is 4 centimeters. Everything here is in centimeters. So I end up pulling 1.57 centimeters of chain to get this to work. So Simple Machines, there it is. They're really great. Thanks for watching.